Dear ladies and gentlemen, in this presentation I will show you highlights and advances in Zatodict for two-phase flows and new features for single-phase flow simulations. But before I come to the actual presentation, I want to introduce myself. My name is Sven Linden and I am the vice head of the software development team. I am responsible for the Lear solver, which is able to perform flow, conduction, diffusion and battery simulations. In addition, I am responsible for the development in Zatodict for two-phase flow simulations. If you have any questions regarding these topics, please feel free to write me an email with your questions. My presentation is divided into 4 parts. First, I will show you the advances of a pore morphology method used in Zatodict and validation results where we compare simulations and measurements. Then I will proceed with a new feature in the Lear solver that can speed up flow simulations drastically. The presentation ends with a summary and an outlook about upcoming features. We will start with the new features in Zatodict. Imagine a water droplet on a plate that is surrounded by air as shown in the image at the bottom. Water and air are not mixed, but separated by a sharp interface. The contact area of a water droplet depends on the wettability, and this depends on the properties of water, air and the plate itself. One extreme is the hydrophobic case, where water wants to minimize its contact area with the plate, with a contact angle of more than 90 degrees. The other extreme is the hydrophilic case, where water wants to maximize its area with a plate with a contact angle of less than 90 degrees. The neutral case is something in between, with a contact angle close to 90 degrees. In Zatodict, we use a pore morphology method to predict the distribution of two fluids in a porous media. There are 2 scenarios that can be simulated. The first one is called imbibition, where in this example, water imbibes the structure having a concave shape. It sucks itself into the structure and external forces are not required. The other one is called drainage, where an external force is required to push water into the pore space of a porous media with a convex shape. The pore morphology method achieves this placement of 2 fluids by using morphological operations. For example, dilation, erosion and different connectivity checks. Therefore, it is not required to solve a complicated partial differential equation, and this results in short runtimes and low memory requirements. Then, the capillary pressure is computed using the Young-Laplace equation. We will have a closer look at the basic algorithm within the next slides. The pore morphology method was first introduced by Hilbert and Miller 20 years ago, and it is still a widely underestimated approach. In the following, I will present some of the milestones within these 2 decades of developments, as highlighted here in this timeline, ranging from modeling drainage in a totally wetting porous media to the computation of relative permeability curve in mixed wet rocks. So I will first explain the pore morphology method in general. Subsequently, I will first focus on the introduction of locally variable contact angles by Schulz et al., allowing to compute two-phase flow within a certain contact angle range for drainage and imbibition computations. Then, I want to firstly introduce our advancement for both an exact representation of contact angles and the possibility to consider contact angles close to 90 degrees, which is rather challenging for numerical approaches with respect to multi-phase flow. In addition, we introduce an extension of a quasi-pore morphology method by a dynamic fluid interface movement, increasing the detail of two-phase flow computations. With these improvements, we may now compute the capillary pressure curve and the relative permeability in mixed wet rocks. In the approach of Hilbert and Miller, the capillary pressure curve is computed via Young-Laplace equation, based on advancing states of fluid distributions. These fluid distributions were inscribed with a 0-degree contact angle, using dilate and erode processes shown here based on an intermediate step in the 2D sample. Here we have mercury in black, air or vacuum in blue, and quartz grains in gray. In order to predict the fluid interface movement, we start off with an initial step where everything is filled with mercury. Then We dilate the solid materials by an air layer with a thickness which is the radius in this equation. Next, the connectivity to the mercury reservoir is checked and non-connected mercury is reassigned to air. Subsequently, the so-called erosion step is performed where an additional mercury layer is introduced with the same thickness, here shown in a purple color. As a result, the new state of fluid distribution is obtained. For drainage setups, this workflow is repeated, and we decrease the radius, resulting in the capillary pressure curve computed via Young-Laplace equation. Before showing simulation results, I will go further into technical details. In 2014, Schulz et al. Published a method to consider contact angles above 0 degrees directly within this geometry. This is realized by adjusting the dilation radius. In this method, r times cosinus of a contact angle. That means we use different radius for dilation and erosion. Now we show this in an animation with a structure where we have two contact angles, 0 degree for grain surfaces shown in a slightly darker color and 40 degree. However, the achieved contact angles were higher than desired, especially for contact angles close to 90 degree and for small objects. This is why we introduce, and how we call it, the true contact angle method, which now takes into account the grain curvature. As a result, contact angles agree, and this allows consideration of contact angles close to 90 degree, which is quite unfavorable for numerical method. But still, as you see in this animation, the monotonic pressure increase in the pore morphology method results in large saturation jumps when the small pore throats are passed. In order to tackle this, we develop the dynamic pore morphology method to extend the quasi-static approach with a dynamic fluid interface movement. This dynamic method features the following. At first, the computation of non-monotonic capillary pressure curves. Secondly, the computation of forced imbibition and ultimately the consideration of mixed wettability. Finally, the method now predicts critical pore filling events as published by Young et al. In 2016. These may now be observed in this animation. First, you will see a touch event on the right hand side. Then you will see a burst event on the left hand side. And finally, you will see an overlap event here in the center. And now, after the mercury has passed the smallest pore throat, the remaining pore space behind that pore throat is not filled at once. Of course, the pore morphology method has many more capabilities. In recent development efforts, we extended the pore morphology method by consideration of mixed wettability. So as a summary, today's capabilities include the computation of capillary pressure curves for alternating cycles of drainage and imbibition, the computation of spontaneous and now also forced imbibition, and spontaneous and forced drainage. And finally, based on the resulting set of fluid distribution, the computation of saturation-dependent properties, such as relative permeability and the resistivity index. This image schematically represents the capabilities that we have now extended by this very important part. So with the pore morphology method, you may now compute the entire hysteresis cycle of primary drainage, imbibition, and secondary drainage. The spontaneous and forced imbibition are simulated by two different kinds of simulations. To make the handling and post-processing easier, we developed a forced imbibition GeoPython app that does all this for you. So you can see the graphical user interface of this GeoPython app on the right side. This app allows to specify contact angles for different regions or minerals within a structure and performs a primary drainage simulation. After that, the app will turn some of the water-wet grain surfaces into all wet surfaces, where oil is in contact with a grain surface. A spontaneous imbibition, and when a forced imbibition simulation is performed, where water invades the structure and displaces oil. Optionally, a secondary spontaneous and forced drainage experiment can also be performed. The alteration of water wet into oil-wet surfaces after the primary drainage is shown in this slide. This alteration is done in a special post-processing step, where water-wet grain surfaces are transformed into oil-wet surfaces, but in large pores only, and only where oil is in contact with a grain surface. This results in a structure that you can see on the right bottom side, with water-wet surfaces in gray and oil-wet surfaces in red. We validated our latest improvements of the pore morphology method by comparing simulation and measurement in a quasi-2D microstructure. First, we have a closer look at the experimental setup. On the left side, you can see an artificial 2D microstructure that consists of cylinders with a diameter of 32 micrometer. The structure is held together with two plexiglass screens with approximately 90-degree contact angle. Thus, we can consider this setup as a 2D experiment. There's an inlet region at the left side where water comes through a pipe and is distributed with several pipe crossings. The water gets into the structure using a pump with a very slow constant inflow rate, such that capillary forces are dominating. 3 different contact angles were used during the experiment: 46 degree, 100 degree and 125 degree. These contact angles could be achieved using air, FC70 and dodecane. The experiments were conducted at the Saarland University by Michael Jung and Ralf Seemann. First, we would like to visually compare microfluidic experiments to the pore morphology method results. Results are shown as animation for the wetting, the neutral and the non-wetting system. You may observe how nicely the computed fluid movements agree with the experiment for all 3 contact angles. In the wetting case, you can observe how the curvature of the interface changes its sign, resulting in a switch between concave and convex shape. This comes from the experimental setup because water is pumped into the system with an external force. The pore morphology method can also predict this kind of behavior very nicely with an experimental implementation. The differences of the trapped FC70 in the neutral system are visible, and this can be attributed to the high sensitivity of neutral systems, so that minor differences in the contact angle may result in different pore filling events. In the non-wetting case on the right-hand side, you can see that the residual dodecane is almost in the exact same location compared to the experiment. But there's also a different pore filling event in the center at the beginning, but overall we got a pretty good match. In a second step, we compared the interfacial area over the saturation for the 3 contact angles. Note that the interfacial area is normalized with a straight domain boundary area after the inlet region. A normalized area of 1 then corresponds to a straight vertical line going from left to right. In addition to the visual agreement, we get a very nice match for all contact angles with respect to this measure. The wetting case is almost a horizontal line. This is clear because the interface in the experiment in the simulation is a deformed but almost straight vertical line. For the neutral and the non-wetting case, the interfacial area grows in a linear way and the slope is equal for the experiment and the simulation. In the next slides, we want to demonstrate a new feature in the Lear solver. I guess that some of you have already noticed that the runtime of the Lear and also the SimpleLFD solver depends on many different properties of the structure and also on the simulation parameters. For example, the runtime is high if the porosity is very small, let's say less than 15%. This is due to the growing complexity of the pore space in low power structures. For Stokes-Brinkmann simulations, the runtime also depends on the permeability of both voxels and the voxel length. For Navier-Stokes simulations, it depends also on the applied velocity or pressure drop. For example, the velocity in, pressure out boundary conditions can also increase the runtime of the Lear solver significantly. Therefore, the Lear solver has high runtimes for tight or low saturated rocks, and these challenges are now tackled with a special solution method called Kurloff method. In the Solver Parameter tab in GeoDict 2022, there's an additional speedup option called Kurloff method, which is available in FlowDict, SATUDict, FilterDict, and in other prediction modules too. This method was originally implemented for the battery Lear solver, but is now also available in the Flow solver too. Here, the biconjugated gradient stabilized method is used under the hood. This method can reduce the runtime for challenging simulations very drastically, but this is paid by an increased memory consumption. Unfortunately, the new method is not always faster than the old method, and therefore we introduce an automatic mode which uses some heuristics to choose the best solution for the user automatically. Of course, it is also possible to explicitly enable or disable the new method. Here, we benchmark the Kurloff method on a tight sandstone, which is part of a benchmark paper by Nishak et al. In 2017. This rock has a very low porosity of 9.5% and is the most challenging structure of this benchmark paper. The Lear with the Kurloff method is compared against the old Lear solver method and the simple FFT solver in GeoDict 21. As you can see in the table, the computed permeabilities are very close, but the runtime could be reduced by more than 80%, so from more than 4 hours to less than 1 hour. And the memory consumption is still much lower compared to the simple FFT solver. Finally, here are computation results for a large mixed wet digital sandstone sample with 1,500 voxels on each side, and thus more than 3 billion voxels in total. The image on the left represents the digital sandstone with dominating water flow paths at residual oil saturation, so at the end of a forced imbibition. The capillary pressure curve shows the primary drainage in a water wet setup and subsequently imbibition in a mixed wet setup. So in between these computations, all wet grain surfaces were introduced based on both the oil phase distribution after primary drainage and the presence of large pores. By computing spontaneous imbibition and the subsequent forced imbibition, we can digitally extract more oil from a mixed wet digital rock. Here the computation with our extended pore morphology method results in an oil residual of 31%. Based on the resulting set of fluid distribution, we can also compute the relative permeability curve, as plotted at the bottom, where we use the Kurloff method to speed up the computation. The entire computation required a runtime of less than 7 days, and in less than 200 GB of working memory in case of our high performance settings used in a 32-core Linux environment. This current runtime of only 7 days for such a large structure is by far faster than hundreds of days required by lab experiments. We approach the end of this presentation. In GeoDict 2022, we have many new features that allow us to simulate two-phase flows more accurately with a dynamic pore morphology method in combination with a true contact angle method. These features allow to simulate spontaneous and forced imbibition, which was not possible before. The no-Kurloff method in the Lear solver can speed up flow simulation significantly for relative and absolute permeability computations. In future GeoDict versions, we want to extend the pore morphology method to be able to predict fluid distributions for higher capillary numbers. The memory requirements of the Kurloff method will be reduced for the Stokes equations, and we want to do more validations on different 2D and 3D structures to demonstrate its predictiveness. And this brings me to the end. Thank you for your attention.